over 0 is something undefined. But what happens as I get closer and closer to 0? Well, you can think of it in a couple ways. One way is to let's think of it in a table of values. Like you can look at a table of values to kind of get an idea of what happens here. If x is approaching 0, well, we can look at what happens as x closes in, gets closer and closer to 0. So what happens to 1 over x squared? Well, we can think about that. You get 0.1 squared would be 0.01, so then 1 over 0.01 would be 100. 1 over 0.01 squared would be 0.0001, so you get 10,000 now, right? And then 1 over 0.001 squared, again, I think we're going to add 2 zeros there, right? You notice that each time it's just getting bigger and bigger the closer I get to 0. Notice that because it's squared here, it would be the same whether or not this x value is positive or negative. So that's kind of one way to see it. What do you guys notice here is that the values of the function values here, what are they doing? They're gonna blow up, right? They just keep getting bigger and bigger and bigger. They get really big very rapidly. So so we could say they blow up. So that's one way to think about it, is to think about what happens if we just literally plug in the values. Or another way is to think about what a graph looks like. I mean, we got the kind of basic idea here, which is that in our graph, if we have values that are getting closer and closer to 0, the graph is just going to get really big. It's going to blow up. Something like that, right? But of course, we know that exactly at 0, we get no values. There's no values at 0. But clearly, we see the graph is going to have like a vertical asymptote there, right? So there's a vertical asymptote at x equals 0. Okay. Now, yeah, let's here's the same thing, right? So you've got the table of values, and you've got the graph. In either case, you can see that as x approaches 0, I've kind of written it here, we can think of this as saying that the limit as x approaches infinity, I'm sorry, the limit as x approaches 0 of 1 over x squared is equal to infinity. Right? Because the values just keep getting bigger and bigger and bigger. They don't really have a bound to how big they can get. So function values here grow unbounded, meaning they don't have any limit to how big those values can get. They just keep getting bigger, right? On the other hand, what happens to the function f of x equals 1 over x squared as x goes to infinity or as x goes to negative infinity? So here I'm going to kind of think of it in the same way. Well, let's look at a table of values and see what we can deduce from that. And here now when I say as x goes to infinity, what we're asking is what happens as x gets large. Or here as x gets large in the negative, as x gets large. As x gets large in the negative direction. All right, so you can think, okay, well, if I put bigger and bigger values in for x, how is the function 1 over x squared going to behave? Well, you notice here, like 1 over 10 squared would be 1 over 100, so that would be 0.01, or 1 over 100 squared would be 0.0001, and so on, right? So these values look like they get smaller and smaller.
So in conclusion, be approaching 0?
Yeah, it looks like they're getting closer and closer to 0 with each bigger value of x, they're getting closer and closer to 0, right? So here as x goes to infinity, it looks like the function values are getting closer to 0. Right? So that's one way to see it, or here let's look at the graph. Again, we can imagine the graph here as x goes to the right, we're saying as x goes to infinity, it looks like it's going to approach 0. It's going to get closer and closer to the x-axis. Or here as it goes to the left, as x goes to negative infinity, it's going to get closer and closer to the x-axis. So it's like now we have a horizontal asymptote at y equals 0. Right? So it's like on the right-hand side, we can think of that, that's telling us that the limit as x approaches infinity is 0. Or here as it goes to the left, that's the limit as x approaches negative infinity is 0. Because notice that here it would be the same thing whether or not this was positive or negative, because again, you're squaring the values, so it comes out to be the same for the negative value as well. Okay, so this is how we're going to start to think about what's going on when we have the sort of asymptotic behavior of these functions. Like what happens as it approaches a vertical asymptote, or how do I describe a horizontal asymptote like we do here. So in 2.4, we're going to focus on infinite limits, which are these ones that are blowing up to infinity. So kind of like the first one where we saw the vertical asymptote. So so this is the same picture, but yeah, notice that these kind of limits we can use to describe these vertical and horizontal asymptotes. Like just looking at this picture, this is just kind of a random picture of some function that has some vertical and horizontal asymptotes. So we have this point here at x equals a where the function blows up to infinity, right? So here we could say that the limit as x approaches a of f of x is equal to infinity, right? So that's what we're calling an infinite limit here. Or here these horizontal, so this is like a vertical asymptote, right? Or these other ones where it's going to negative infinity and it approaches some line here, L. Or here as it goes to positive infinity, it's approaching some other line, M. Right, so these are limits at infinity, but these are really horizontal asymptotes, right? Because we see that the limit as x approaches negative infinity, what happened? Come back. Okay, well, I lost everything. I'm not sure what happened. Okay, anyways. Okay, so I'm just rewriting what I had before because I accidentally erased it and I have no idea how to bring it back. But I don't know. I keep trying to figure out how I can make it not erase things, but it does it regardless of what I do. So anyway, so this was a horizontal asymptote. And this was a different horizontal asymptote. Anyways, so this is what we're going to focus on in this section are the vertical asymptotes where the function blows up as it approaches some value. Okay, so that'll be our goal, is to try and figure out how we can analyze functions where it behaves like this. So that's one thing to look out for, is when will the function blow up? And we can kind of look for cases where, like in the previous, like the simpler example that we saw here, let me flip back a few slides. Like notice that what made this function blow up was the fact that the numerator was some non-zero value, but the denominator was getting closer and closer to 0, right? So when you have something like that, when you've got, you know, like a function like this, f of x over t of x, where it goes to something that's not 0 up here, but the bottom does go to 0, this is usually when we're going to have the function blows up. Right, because we can kind of see here, when you divide by smaller and smaller numbers, right? If I'm dividing by something that's getting smaller and smaller and smaller and smaller, when I'm dividing, the quotient is actually going to get bigger and bigger and bigger and bigger, right? The quotient's going to explode. It's going to get huge as the denominator gets smaller and smaller and smaller. Okay, so that's the way we're going to think about it, and you can look out for things like this, or that behave similar to this. We'll look at maybe more varied examples, but this is sort of a simplistic case where we can imagine it very easily, how that behavior works. Okay, so let me look at just the basic definition of what it means to say that the limit goes to infinity. Suppose f is defined for all x near a if f of x grows arbitrarily large for all x sufficiently close but not equal to a. We write the limit as x approaches a of f of x equals infinity. Okay, so grows arbitrarily large is the key thing here. We can be a little bit more technical about what that means, but for us, we can just think of it, it just grows unbounded. So grows arbitrarily large, it just keeps growing unbounded. In other words, there's no bound to how large that value gets. It just keeps getting bigger and bigger and bigger. Okay, so we say, yeah, the limit as x approaches a of f of x is infinity. If f of x is negative and grows arbitrarily large in magnitude, so in other words, it's getting large but in the negative direction, right? Then we say the limit as x approaches a of f of x is negative infinity. Okay, so it's negative and grows arbitrarily large in magnitude. So again, it's just grows unbounded in the negative direction. Okay. And a technical thing that we want to keep in mind, in either of these cases, the limit really does not exist. When we write the limit as x approaches a of f of x equals infinity is sort of specifying something specific about how the function behaves there. But of course, we know that infinity itself is not a number, so this is not really approaching any one particular value, right? So in either of these cases, we can be more technical and say that the limit does not exist, but we're being a little bit more specific about its behavior when we write this. We're kind of describing how the function really behaves as x approaches a is going to infinity, meaning it's blowing up to infinity. Or as x approaches a, it blows up to negative infinity. So that means, right, it's going in the downward direction. So let me just demonstrate here with an example that we can try and think about. For instance, what happens here as x approaches 1 for x over x squared minus 1 squared? So what I want to do actually is think about, if we want to analyze this, is to think about the numerator and denominator separately. And in fact here, I'm going to approach from two directions, one from the left and one from the right, and see what happens there. But anyway, so let's look at the first one here. As x approaches 1, the numerator is going to be just x. So what is it approaching in the numerator? It's approaching 1, right? Now, what I want you guys to think about is what is happening here.
0 in the denominator.
Sorry?
0 in the denominator.
Good. So it's approaching 0 in the denominator. What can we say about the sign of the function, or the sign of the values in the denominator? In other words, am I always going to have a positive number or a negative number down here?
It can always be factored, then it could be a positive after the squared.
Yeah, because you got the square on the outside here, it's always going to be positive. So the denominator approaches 0 and is always positive. Right? It approaches 0 and is always positive. And the reason why I know it's always positive is because of this power of 2 here makes it always positive. Okay, otherwise, if that square wasn't there, it might not always be positive. In fact, you could see that if I were to put in a value of x that's slightly smaller than 1, if that square weren't there, you would actually have a negative value, because you'd have something smaller than 1 minus 1 would have to be a negative value. Okay, but because it's squared, we know it's always positive. So we know that here in the denominator, it's approaching 0, but it's approaching from the positive side, right? From the right side. So this is kind of like a way for me to analyze it or to think about it, because now this tells me that it's going to positive infinity. Because I know 1 on the top is not 0, and then something that goes to 0 on the bottom, sort of like thinking about that example, 1 over x squared, right? We had something similar, right? Where it's 1 on the top, but then it gets closer and closer to 0 in the denominator. So that quotient is just going to blow up. It's going to get huge. So that's how I want you guys to think about it, is that this here is just one way of notating that telling us that the fraction blows up as x approaches 1 from the left here. Okay, so it goes to positive infinity from that side. And I think we can probably make the same argument here. In other words, approaching from the right doesn't really make a difference because again, that square here ensures that it's always going to be positive in the denominator. So putting these two pieces together, the limit as x approaches 1 of x over x squared minus 1 squared, right? Since it approaches positive infinity from the left, positive infinity from the right, we'll just say it equals to positive infinity. Okay, so this is the way I like to analyze it, because it kind of helps me see, okay, if this were approaching 0 from the negative side, then I know this fraction would always be negative. So it wouldn't blow up to positive infinity, it would blow up to negative infinity. Okay. Here, I think almost the same exact argument is going to work for this limit as well. So we can write it out, but you'll see it's almost the same exact argument here. So if I take the limit as x approaches -1 from the right, right? Same idea, because up here you've got something where it's 1 over something that's approaching 0 in the denominator, but from the positive side, we know that this is going to be positive infinity. And if I take the limit as x approaches -1 from the left, same argument. Here we've got something that is approaching 1, or sorry, actually, I messed that up. It's going to be -1 in the top, right? Because now we're approaching -1, x equals -1, right? So yeah, my bad. We're approaching -1 in the top, but the bottom is still approaching negative infinity, or sorry, the bottom is still approaching 0 from the positive side. Okay, so let me fix that. So this should be negative infinity. Same here. This is approaching -1 in the top. The bottom is approaching 0, right? If I put -1 in for x here, you get something that's going to be 0 there in the bottom. But it's approaching 0 from the positive side, right? So the way I write that is I just think of it like that, right? So we see this is also approaching negative infinity, because you got a negative number over a positive number is always negative. Okay, so again, putting these two pieces together, that means that when I take the limit as x approaches -1, I get negative infinity. Okay. So, oh, and actually what I did here was I analyzed it just using using the function itself. Although reading the instructions here, I probably should have read this last part. It says to use the graph of the function. Actually, this is going to be much easier. So let me just kind of show you guys what the graph looks like. So if I'm using the graph of the function, it's actually much simpler. You just see that there's a vertical asymptote there at x equals 1. So as x approaches 1, it's going to blow up to infinity. Or here, as x approaches -1, it's going to blow up to negative infinity. So that's kind of how the graph looks when it's blowing up, right? It's got the vertical asymptote at x equals 1. So as x gets closer and closer to 1, the function values there just blow up. Okay, so here the same thing as x approaches -1. So as x gets closer to -1, function values are going to go down to negative infinity. Okay, so yeah, actually, if you guys were confused with what I just did here, is because yeah, I was getting a little bit ahead of myself. I think we were going to do something a little bit simpler first, but here the instructions were to use a graph of the function. But anyway, so you can kind of get a little bit of a preview into how we're going to do this in general. But when you see the graph, it should be kind of clear that when I have this vertical asymptote like at x equals 1, right, it's just blowing up to infinity. Or when I have this vertical asymptote at x equals -1, it's just blowing up to negative infinity. Okay, does that make sense? Can you guys see how that works when you have the graph? Using the graph, is it easy to see, or is that kind of confusing? Do you guys have questions about that?
Professor, I'm kind of. Oh, sorry.
Yeah, go ahead.
I'm kind of confused on the 0 plus in the denominator on the previous slide, like what that means.
Yeah, I was using that as a way of describing the behavior. So, I mean, I'll explain this maybe again in another example later that's maybe a little bit simpler. But yeah, the idea is that here we see the denominators approaching 0, but it's always positive. So the little plus reminds me that it's always positive. Because you got the square there means that whatever value of x I put in here is always going to be positive because it's squared. So you can think of it as approaching 0, but from the positive side.
Thank you.
So I'll do some more examples of this in a minute, but here the graph should be a little bit easier to use when you're finding the infinite limits. Yeah. So I think, yeah, sorry, I apologize. I got a little bit ahead of myself on that example because I didn't really explain what was going on with the left and the right hand limit. So let's suppose that we have the limit as x approaches a of f of x from the right, or x approaches a from the right side. If we say that that's equal to infinity, what it means is it just blows up from the right side. Or if the limit as x approaches a from the right goes to negative infinity, then it's just blowing up to negative infinity, but only from the right side. So the picture there is that if it blows up from the right side, like this, you can think of it, that's the limit as x approaches a from the right goes to infinity. or if it blows up in the negative direction, something like this from the right, then we're saying here the limit as x approaches a from the right is equal to negative infinity, right? And same idea from the left. If I take the limit as x approaches a from the left, and it blows up to infinity, right? You get something like that. Or if it goes to negative infinity as it approaches from the left, maybe you get a graph that looks like this. Okay, so thinking about it on one side or the other, in either case, in any of these four cases, we have a vertical asymptote at A. Okay, so that's how we're thinking of what a vertical asymptote is. It approaches from either one side or the other, and it goes to infinity or negative infinity. That means we have a vertical asymptote there. So, okay, so here's the same pictures that I just drew, but so when I'm approaching from the right, either it goes to positive infinity or negative infinity. In either case, we have a vertical asymptote. It approaches A from the left, and it goes to positive infinity or negative infinity. We have a vertical asymptote there, right? And yeah, so that's what our vertical asymptote is by definition. It's if the limit as x approaches A is positive or negative infinity, the limit as x approaches A from the right is positive or negative infinity, or the limit as x approaches A from the left is positive or negative infinity. In any of these cases, we know that the line x equals A must be a vertical asymptote of the graph. So it could be any of those four cases that we saw before. And we would know that in any of those cases, then it has to have a vertical asymptote. So that's kind of an important way to think about how the function behaves, is to think if I have a function that blows up or goes to infinity as it approaches some value, then that value really is a vertical asymptote in the graph. So let's just kind of use the graph here to describe the vertical asymptotes. And again, here we can just look at the graph. You can see that at x equals 1, we have this vertical asymptote. As x approaches 1 from the left and as x approaches 1 from the right, from both sides, it's going to positive infinity. So, right, so it goes to infinity. Oops. As x goes to 1 from the left, oops. And as x goes to 1 from the right. So it's going to positive infinity from both sides. So that's why we say here the limit as x approaches 1 is infinity. Okay. The limit as x approaches 3 from the left, you notice goes down, right? So it's going down to negative infinity here. So this is negative infinity. Oh, this should be a little plus here. I think I maybe left out the plus. The limit as x approaches 3 from the right side. If we look at the graph, it's going up to positive infinity. Okay, so these are looking at it from the one side. So if I were to write, notice if I were to write the limit as x approaches 3 without indicating a direction, could I say it's equal to infinity, or could I say it's equal to negative infinity? How would I describe this limit here?
Wouldn't exist.
Correct, yeah. So you could just say it doesn't exist, because actually positive infinity and negative infinity are different types of infinity. So if they were both going to the same type of infinity, then you could say that this is equal to, infinity, sort of like what we said here, right? From the left and from the right, they're both going to positive infinity for the first one, for part A. So we just said that this one's equal to infinity, but this one, from the left and from the right, they're going to different types of infinity. So we just say it doesn't exist, right? So actually, that doesn't really kind of tell you very much about it. It kind of makes it easier to describe what's really going on if I look at the left and the right side separately, because that kind of gives me more information, right? I get a more rich picture if I include both the left and the right hand limit to describe how it behaves at x equals 3. Okay, so yeah, so let's work on how we can actually do the analysis. So this was kind of the thing I was trying to show you guys earlier, that right, if I just have a function, in this case 5 plus x over x, and I want to know what happens as x goes to 0 from the right side. So in the top, you got something that's going to 5 plus 0, right? And in the bottom, you got something that's going to 0, right? And since it's approaching from the right side, well, we know that this is approaching from values of x that are bigger than 0. So those are always going to be positive values there, right? And so we got something that's approaching 5 in the top and approaching 0 in the denominator. So this is really going to be going to positive infinity. One way you can visualize this is you can think about, okay, well, what happens if I were to just kind of make my table of values and just take values that get closer to closer to 0 from the right side? Well, you got something that's going to get closer and closer to 5 in the top, right? So like 5.1 over 0.1, 5.01 over 0.01, 5.001 over 0.001. But in either case, what happens is we get something that's getting closer and closer to 5, but dividing by something that gets really, really small. And since the divisor here is getting really tiny, the overall quotient is going to get really big. Okay. So that's that's one way to think of it, right? Is that as x gets really tiny, as it gets really close to 0, you get something that is getting really big when we divide, right? So here's kind of like maybe a bit better picture. You get something down here, 501, 5001, 50,001. Right, as we get closer and closer to 0, these values are just getting bigger and bigger and bigger, right? So we would say that that the limit as x approaches 0 from the right of 5 plus x over x is equal to infinity. Okay, so this is how I'm going to kind of analyze it. I'm going to think about how the numerator and denominator behave as the value of x approaches whatever number, right? So in this case, as it approaches 0 from the right, how do the numerator and denominator behave? Kind of tells us something about how the quotient comes out. So let me do something similar here. Let's look at these examples. We've got the limit as x approaches 3 from the right of 2 minus 5x over x minus 3. So let's just think of it like what happens to 2 minus 5x. Well, this is going to just approach 2 minus 5 times 3, right? So it's going to approach 2 minus 15, or negative 13. What about x minus 3? What happens to that?
0.
Okay, so you got something that's approaching 3 from the right, minus 3. Is this going to be a positive or a negative value when I do something that's so think of 3 plus here. This is really something that's a little bigger than 3.
Positive, right?
Yeah. So 3 plus is a little bigger than 3. So this is really approaching 0, but from the right side. Okay. So with that, then we have that 2 minus 5x over x minus 3 is going to be approaching negative 13 over something that's approaching 0 from the positive side. So would you guys say this is approaching positive infinity or negative infinity?
Negative.
Yeah, good. It's approaching negative infinity because you got a negative 13 on the top, and then something that gets closer and closer to 0 from the positive side. So you got a negative number divided by a positive number.
What?
So think of it like this is always negative. This quotient is always negative. Because you got a negative number divided by a positive number when we're approaching from the right. Okay, therefore, right, we would say that this goes to negative infinity because you got something that is getting really tiny in the bottom, but something that's getting closer and closer to 13 or negative 13 in the top. Okay, so this is going to be negative infinity. Okay. So we'll do the same analysis over here, right? So let's think as x goes to negative, or sorry, as x goes to 3 from the left now. What happens to, again, 2 minus 5x? Top will get closer to 2 minus 5 times 3, which is 2 minus 15 is 13. Or sorry, negative 13. Okay. How about x minus 3? So now we're approaching from the left. So we got something that's approaching 3 from the left minus 3. So 3 minus 3, of course, is approaching 0, but is it approaching 0 from the positive side or from the negative side?
On the negative side.
From the negative side, right? So I shouldn't put plus there. I should put minus there. Right, so again, you want to think of it like 3 minus here is a number that's a little bit smaller than smaller than 3. When we're approaching 3 from the left, we're assuming it's less than 3. So maybe if it helps mentally, put in a number there that's smaller than 3. 2.9 minus 3 is a negative number, right? So it's approaching 0 and is negative. So it's like it's approaching 0 from the negative side, right? So then putting those pieces together, we have 2 minus 5x over x minus 3 is going to approach negative 13 over 0 from the left, which is really approaching, what would you guys say here? Is it approaching positive infinity or negative infinity now?
Positive, since there's two negatives.
Very good. Yeah, so I've got a negative number on the top divided by another negative number on the bottom. So it'll approach positive infinity. So this one will be positive. So you're dividing negative by negative. Question?
Yeah. Since one side is. Oh wait, no, never mind. I just answered my own question.
Okay.
Thank
Yeah. So we've got negative divided by negative. This is always positive. So, negative over negative. Let's try one more sort of similar type of analysis. Maybe slightly more complicated looking, but we'll approach it the same exact way. Right? I want to describe what happens here as x approaches negative 4 from the right. So what I'll do again is just think about how if as x goes to negative 4 from the right, what happens to the numerator? Well, you can plug in negative 4 if you want. Let me see. I'm not sure if I can do this in my head. So that's 64 plus 80.
Would you like the answer?
24. Yeah, please.
I got 168.
Sounds about right. Yeah, so sounds about right. Yeah, you got 64 plus 80 plus 24. Yeah. Cool. So that means we got something that's approaching a positive value there in the numerator. then let's look at the denominator, negative x cubed minus 4x squared. Here again, approaching negative 4 from the right, so we're going to do negative. So actually, what I might do here before I plug in, because it's going to be helpful to think about whether or not we're getting a negative or positive value here when we're approaching from the right, because that can be tricky. That can be the tricky part here. So what I'll do is actually, or I'll factor out the negative x squared. And then I have x minus 4 left over, right? You guys see that? So now when I analyze these two pieces, now it's a little bit easier to kind of see in particular how this guy is going to behave, right? Because as x approaches 4 from the right, or sorry, as x approaches negative 4 from the right, so you can imagine here, x approaches negative 4 from the right, we're plugging in a value, we'll say the values of x are going to be slightly bigger are slightly bigger than negative 4. What's a value of x that's bigger than negative 4? Something bigger than negative 4. What do you guys think? Any value that's bigger than negative 4.
4? Can you use positive 4?
Okay, yeah, but there may be something closer to 4, or closer to
negative 3.
Yeah, say negative 3.9 or negative 3, right? So if I do that, if I do negative 3 minus 4, oh, actually, okay, I see what I did wrong here. What did I do wrong here? This should be a plus, right? My bad. So, sorry, I factored out the minus sign, right? So that should be a plus there, my bad. Anyways, but anyway, yeah, so we're approaching from values of x that are slightly bigger than 4. So it'll be negative 3 plus 4. Or maybe it makes more sense, in my opinion, to think about values that are getting closer to 4. Sorry, getting closer to negative 4. So like negative 3.9 plus 4. Notice this is a positive value. And as this value gets closer and closer to negative 4, it's going to always be positive, but it's going to get closer to 0. Okay, so with that in mind, this is going to approach, so negative number, right? Because I got negative times negative 4 squared, and then times something here that's approaching 0 from the positive side. Okay, so you've got negative 16 times 0, which is going to be approaching 0 from the negative side. Okay, so with that just kind of breakdown here, what we notice is that this is going to approach 0 from the negative side as x approaches negative 4 from the right, just in that denominator, right? So with that, we can say now just the whole thing. Right, let me squeeze it over here. So the whole thing, negative x cubed plus 5x squared minus 6x over negative x cubed minus 4x squared is going to approach 168 in the top. and then it's going to approach 0, but from the negative side in the bottom. So that's going to be negative infinity. So that's my answer.